Thank you. Thanks for showing up this morning. I have to start with a story. I'm impressed that the room is packed. So I was playing in a rather unsuccessful heavy metal band for quite some years, and I always dreamed about performing. Life can be very ironic. You start working on quantum computers and diamonds, and people show up to your performance. Anyway, so I have to start with a little disclaimer, and I mean that from the bottom of my heart. I'm a physicist, or more precise, I'm a material scientist, and with that, I have a strong background when it comes to materials and diamonds. My background is not so strong when it comes to the things you are interested in, quantum algorithms and stuff, although I will talk a little bit about that. Please be kind when it comes to the question and answer part of this talk. Anyway, let's start. Whenever you take a look at the concepts of future computers, of course it makes sense to take a look back on the computers that were there before. And of course, every one of you know this diagram. It's Moore's law. And this diagram, it shows, this is the time scale, and it shows the numbers of transistors on a microchip. And this diagram never fails to impress me, because Moore he wrote a paper actually on that, and he claimed that the number of transistors will double every 24 months, and he claimed that 1965. So back here, down here, at a time where we were only talking about a few thousand transistors, and this law is still true when it comes to the more modern computers, where we have billions of transistors. So that's quite impressive, this vision that he had. How is that possible? How could we improve from a few thousand to billions of transistors on a microchip? Well, pretty straightforward and pretty easily by scaling down the size of the transistors, of course. If we take a look, this is again Moore's law, the same, but now I show you the feature size, the transistor size, basically, that you can find on such microchips. And we started in the 70s with sizes of a few microns, 10 microns, that would compare to your red blood cells, to the size of your red blood cells. And we're now down to 22 nanometers. That's extremely small. And we're closing in to sizes like the diameter of your DNA, which is like 2 nanometers thick or wide. How was that possible? Well, that was possible by simply scaling. You had a technology, you had a method of producing these transistors, and you slightly improved them, and so you were able to reduce the feature size. Can we go on like this forever? Obviously, no. I actually believe we already have seen the lowest limit that we can reach. There was a work group in 2012, I guess. They produced a transistor made out of one single phosphorus atom in a silicon matrix. At least for me, it's hard to believe that we can get any smaller than one single atom. I mean, in the end, you need to store the electron, the charge carrier, somewhere. So I think we hit bottom already. But the problem is not that we will at one time really, I mean, that was an experiment in a laboratory that is obviously not a ready available microchip yet, but still maybe we have seen the lowest limit that we can reach. But nevertheless, already going there to the lowest limits will make us face some problems, and these problems will arise here when the feature size gets even slower, because then we have to deal with quantum effects. And what that means, I wanted to show you on the next slide with an easy picture again. Let's start with the German Autobahn. For those of you who are not coming from Germany, German Autobahns are great because you can drive as fast as you want. And that is not a problem, as long as everybody stays on the lanes that is, or I should say, where you are supposed to be. So if you're traveling in that direction, you better stay on the right side of the German Autobahn. If you are somehow able to go over this barrier here in the middle and try to appear on this side, you and your opposite car drivers will have some problems. Same is true, of course, for microchips. They are some are, or can be compared to autobahns. We have these electrons, the charge carriers, running around somewhere here in these connectors and stuff, transistors. As long as they stay where we want them to be, everything is fine. But as soon as we come to really small sizes, small scales, something really strange is happening. And this is a beautiful simulation of Jean-Christophe Benoit, showing you one electron. This is this blurrish, whitish thing, moving towards a barrier that this electron cannot surpass. And what you see here, most of the electron is reflected, or the electron seems to be reflected. But what you also can see is that a small whitish blob is actually tunneling through this barrier where the electron is not supposed to tunnel through. So you see, when we come to small scales, we are heading into problems because electrons are freely jumping around, and that is not what we want. So the question is, if we cannot avoid quantum mechanics, why don't we use it? Is there a way to use these effects? And this is basically what I want to talk today about. My presentation is in two parts. The first part is basic concepts of quantum mechanics. But there won't be any equations, so I will stick to pictures and nice metaphors. And the part two will be a real realization of quantum computers, how we try to do this with diamonds. Okay, I promised you pictures, so we start with this picture. Manuel Neuer, I love him dearly. He made us world champion, but I also envy him a bit, because the game he's playing is fairly simple, while I'm dealing with quantum mechanics, and that's fairly not simple. And this guy is earning much more money than me. I not even have a permanent position at a university. But anyway, let's take a look at classical soccer. Manuel Neuer, easy game. He needs two information to play this easy game. He needs to know where the ball is. So he needs to know where is the position of the ball. And he needs to know where is the ball going. So the velocity, that's what physicists call it, velocity of the ball. So that means speed and direction. So two information. Very easy game. Now we go to quantum soccer. That's harder. Manuel now needs to choose whether or not he wants to know the position. Then he absolutely don't know where the ball is going. Or he chooses to know where the ball is going. Then he has no idea where the ball is. You see, the game is getting harder. No World Cup for us in the case of quantum soccer. So, being more precise now, we can compare it now. We can compare classical physics now with quantum physics. As we have seen, classical physics, so if we're talking about balls, it's perfectly fine that we know the position and the velocity of a particle. That changes with quantum physics. Let's go back to the electron. You see here this blurrish reddish electron, and we know. Let's say we know exactly the velocity of the particle. We know where it is going and at which speed. Then we don't know the position of the electron actually. So this is not how a physicist would draw it. We like diagrams, so we would do something like this here. The x-axis is the position of the electron. The W here means the probability that the electron is actually at that point. So it is very likely that it's somewhere here, but there's still the chance that it's right of there or left of there. So it can be somewhere here with more or less probability. Werner Heisenberg, German physicist, was working on that, was a founder of this theory. And this is Heisenberg's uncertainty principle. That simply means the uncertainty of the position times the uncertainty of the momentum, which is more or less the velocity, is always bigger or equals to this constant. This is simply a number. This tells us something about nature, and this is really interesting. This is an intrinsic uncertainty which lies in nature. So this is not because our microscopes are too bad, or we are not looking close enough where the electron is, or not fast enough. This is an intrinsic uncertainty. When it comes to small particles, this is how nature is behaving, and this is really or you would not expect that, I would say. Now, with this simple principle, we already can explain tunneling, quantum tunneling, the thing that we talked about already. The electron coming close to a barrier, to an energy barrier, or let's say it's a wall. And usually you would expect that a particle cannot go through the barrier. But in fact, now you see this diagram that we physicists love. And now you see the probability says it's very probable that the electron is on the left side of the barrier. But there's still a small probability that the electron is actually on the other side. And this is the reason why tunneling really happens and can be measured, just because there is a mathematical probability that the particle is on the right side. It really appears on the right side every once in a while. And this is what I already showed you with this beautiful, beautiful animation and simulation by Jean-Christophe Benoit. Yeah, this is physicist humor. Told you Heisenberg. This is actually a toilet in my faculty. This is what physicists laugh about, but anyway. Okay, we talked about uncertainty, uncertainty in position and velocities, but this is not only true for positions and velocities, but also for quantum states. What I mean with that, let's talk about information. So a classical bit you all know can be turned on, turned off, or in binary code it can be 1 or 0. With quantum bits it's a little bit different, and we already talked about uncertainty, and the same is true here for quantum bits if we talk about states of quantum bits. You see here the quantum bit, the qubit, can also be 1 or 0, but it can be everything in between. That's what physicists call a superposition. These superpositions are really, excuse my language, fickle bitches. You only have a superposition when you don't look at the qubit. So you are not allowed to make any measurements. As soon as you make a measurement, you end up with a clear 1 or 0 as a state for the qubit. But as long as you don't look inside the box, no information in, no information out, then you have the superposition, this any state in between, and you can actually work with this superposition. So is that the same as when I would take a coin, flip that coin, catch it in front of 400 people, and keep my hand covering up the coin? Is that a superposition? No, it is not. The state of my coin is described by basically probability. It's 50-50. Either it is heads or it's tails. And of course my ignorance, because I haven't looked yet. But the fate of the coin is already chosen. That's quite philosophical. Okay, the fate is chosen. If I uncover it, I see the result, but the result was there before. This is not true for superpositions of qubits. As long as we haven't looked, the fate of the qubit wasn't decided yet. There is no record. There is no decision made yet. And this is what makes qubits more powerful than, or that's one reason why there lies power in the concept of quantum mechanics. Now let's talk about, we already talked about qubits, but the question you could ask now is, of course, what is a qubit? So, I mean, in real life, where can I see one? We start again with a classical bit comparison, 1 and 0. We could take this spinning tops as yet another picture. Either it is facing down and turning anti-clockwise, or it is facing up and it's turning clockwise. The same is true. Actually, this is not true. For qubits, qubits are small particles, and small particles like electrons, protons, photons, they have a property that physicists call the quantum spin. You should not mix this spin with a quantum spin, so actually the electron is not turning and spinning. But still, it's a nice picture, so we use it. But what you really can measure and see is that qubits have a small magnetic field. So they have a north pole and a south pole. And that's pretty, that comes handy because we now can manipulate the state of the qubit. If we take a rather strong magnetic field and we bring in our qubit, it will very likely align in the position of the lowest energy. That means, of course, the north pole of the magnet will face to the south, and the south pole of our little qubit magnet will face to the north. Just like a compass needle, of course, you can open the compass and invest a little bit of energy and turn the compass needle in the other direction. The same you can do here. You can invest a little bit of energy and turn the needle the other way around. This is another state, it's a higher energy state, and we also use that in our qubits. So you can produce 1 and 0 positions of your qubit. And we come back to that later when I show you how we actually do this. So then we are at a point where we need two information. So how probable is it that we find our qubit in a up-facing position, and how probable is it that it will face down? So two numbers, and we can describe our qubit. That's not very exciting, I would say, but it gets exciting when we start looking at more than one qubit, because then is something very interesting happening. Let's start first again with two-bit systems. Both spins, or this here, both down, one down, up, down, up, and of course, you know, 1, 1, 2, 2, 0, 0. So although the system, our two classical bit system, can have 4 states, we need 2 information to wholly describe the system. You need 2 information. What is the state of the first bit? What is the state of the second bit? That gets a little bit more complicated when we come to qubits, and I spare you even more, I spare me the mathematics behind it. 2-qubit system, it can be easy. Let's say this case here, both qubits facing up, very easy. 2 qubits facing down, very easy. But this here isn't easy at all. This is what physicists call entanglement. In that state, the one qubit is facing up, the other one is facing down, and the 2-qubit system, the entangled qubit system, is perfectly free in whatever direction it want to face. We were already talking about that when I introduced the superposition, but the same is here, the entanglement. Now we have 2 qubits, and they can face in whatever direction they want. So they are more or less perfectly free, with one exception. The one qubit is facing the one way, the other one is facing the other way. So you see, you need more information to describe such a system. In fact, for a 2-qubit system, you need 4 information. So A, D, and this entanglement states B and C, which comes out of rather complicated mathematical calculations. 4 informations. for 2 qubits. But it's getting more extreme if we are talking about more than 1 or 2 bits versus 2 qubits. You see here the classical bit system. Of course, you already know 10 normal classical bits. You need 10 information, n information for n bits. But for qubits, it's 2 to the power of n information. So this system is getting rather complicated fast. In fact, if we would succeed in having 300 perfectly entangled qubits, this number here, 2 to the power of 300, is so big that you need more information than we have particles in the known universe to describe this system. So you see, the system is getting complicated. But of course, you can formulate it the other way around. We have a complicated system, so we can work on complicated problems. And I touch back on that, I guess, on the next slide. But first, I have to show you one more thing concerning this strange nature of qubits. Again, we start with the 8-bit register. If you want to do calculations or if you want to rewrite the information in such a register, you need steps, process steps. So that takes time. So calculations, rewriting of the register positions here takes you time. In entangled systems, in qubit superposition or entangled qubit systems, this looks a little bit different, and I have already told you about that. I told you about this entanglement, that we have these 2 entangled qubits, and that they are not independent of each other. So if the one is facing in the one direction, the other one is facing in the other direction. And that has a consequence in so far that if you manipulate one of those qubits, you manipulate all of them immediately. And that's, of course, there lies a real power, because you can in parallel do operations that you couldn't do in a classical computer. Are quantum computers faster for every problem, for all the problems? Well, no, they're not. In fact, for most of the problems, they're actually slower. If you would sit on your couch and stream a movie, the quantum computer wouldn't have any advantage. There are specific problems where quantum computers have the edge over classical computers. And that's problems that you are, of course, familiar with. For example, the public key encryption protocol, which basically is based on the fact that it's very, very easy to take 2 integer numbers, prime numbers, and multiply them. And everybody of you could do that within a minute, I guess, and tell me that the result is this large number here. It is more complicated to do it the other way around. If I would ask you what are the prime numbers that, if multiplied, give this number, this is incredibly hard. And so hard that classical computers need thousands of years to do that. And a quantum computer would only need some minutes to do that. The reason is that that a lot of calculations can be processed in parallel. Other non-reciprocal problems are also problems that seems to be very suitable for quantum computers. For example, this here, the phone book problem. It is very easy for you if I ask you for I give you a telephone book and ask you for the number of John Doe. You could easily tell me the number. If I just give you a number and you are supposed to find me the name from this phone book, that will be rather hard. And this again is a problem that can be solved with quantum computers more effectively. In fact, I told you I'm not really strong in quantum algorithms, but I show you at least the more famous algorithms that were found. And they were actually found quite some years ago, 1994 and 1996. The Shor algorithms algorithm, which is for integer factorization, I talked about. You see here, if we take a typical example, then you see that a classical computer would need 10 to the power of 19 steps, while the quantum computer only needs around 90 steps. And the same for the phone book. 60 million entries. The only strategy, basically, that a classical computer have is starting at A and go through till he finds the number. No, he's not starting with A, but he's starting with a telephone number. But he's starting with the first entry and go through the entries. And at one time, he by chance finds the right name to the number. And the quantum computer is faster there with a lot of less steps to find the right name to a number. So I told you I'm not strong here, but the message I want to send with this picture is this here, the bottom line. We have the algorithms, so we need hardware now. So give us the hardware. And we're taking, if we are talking about the realization of a quantum computer, there was a nice paper from a guy from the University of Aachen, Di Vincenzo. He established the Di Vincenzo criteria for quantum computers. So he said, if we want to realize quantum computers, we need to realize or address these problems for quantum computers. And they are pretty obvious. We need well-defined qubits, of course. We need qubits that we can trap, that we keep at place. And the next thing is we need to initialize them. We need to give them a pure state, either superposition or tell them B1 or B0. We need quantum gates, of course, to do operations, algorithms. We need measurements to read out our qubits, whether or not they are 1 or 0 at the end of our calculation. And we need long coherence times. That means those, I told you already, our superpositions, our qubits, they're fickle and they act strange and randomly at times. So we need qubits that are rather stable. Okay. We need to address all of this in the next slides. But let's start with a short history of quantum computing here. 2001, IBM showed the first real quantum computer, an NMR computer, nuclear magnetic resonance computer, and they actually had a Shor algorithm running on it. They used the Shor algorithm to do this factorization problem I showed you. And the incredible number they were able to process was find the prime numbers of this number. Is anybody capable of doing that here? Yeah, right. The gentleman said not at this time. But usually I would say you are as good as a quantum computer when it's not that early on a Congress day. Okay, I give you the result. It's 3 and 5. Oh man, I felt with my heavy metal band, and now I prepared a good-looking presentation, and all I need to do to impress you is giving you the prime numbers of. I really have to rethink my life after this Congress. Okay, that was 2001. 2005, 2011, incremental improvements of the quantum computers. 2011, HiFi China, 4 qubits, giving you the number of, or the prime numbers of this number. These are other implementations of quantum computers. As you know, I will talk now about diamonds and quantum computers with diamonds. But if you're interested in these implementations, I strongly suggest, if you haven't seen it, the wonderful presentation, Let's Build a Quantum Computer by Andreas Deves on this at this Congress. Rewatch it if you haven't seen it, because it was really fascinating to see those concepts. The problem, Oh, I messed my joke. You don't have... Okay, what I wanted to say is, although Andreas realized a quantum computer here with these methods, they have some kind of drawback. All these implementations are rather complicated. You need large lasers, you need vacuum chambers, you need strong electromagnetic fields to trap your qubits. So this is nothing that you would put on your office desk. So this is what I call, and please act surprised, badass physics. So of course, physicists were looking for alternatives, and they were pretty surprised to find an alternative here in diamonds, actually. Diamonds have extremely stable qubits at room temperature. You don't even need to cool down your devices. So this is something where scientists are really looking at and hoping for improvement in the field of quantum computers, because the diamond has such incredible properties. And I will tell you now why they are so incredible. But actually, what we need is not, we don't need perfect diamonds, but we need diamonds with small defects. And I like this quote here from Colin Humphreys, a physicist: "Crystals are like people. It's the defects in them which tend to make them interesting." I like that very much, because we don't need perfect diamonds. We need diamonds with specific defects in them. This is a diamond lattice. Diamond is made out of carbon. And what you see here is the special defect I'm talking about, the NV center. And the N stands for nitrogen, and the V stands for vacancy or void, so a missing carbon atom. So that's what you see here. There's the nitrogen atom, and there is the void, the missing, the vacancy, the missing carbon atom. And this structure in a diamond, the NV center, has remarkable properties. They are a very excellent trap for electrons. And we already talked about that electrons have a quantum spin. So we have a trap for electrons. The electron stays at that position, and it's rather stable for some reasons. Those qubits have a long coherence time at room temperature in diamond. Question now, of course, is, let's start with this here. We succeeded with the first point. We have well-defined qubits. Now the question, of course, is, can we measure them? Can we initialize them? So first, measuring them. Can we measure the state? First, an easy picture. What physicists do when they want to measure something is they use lasers. So we shine a laser on these NV centers, and we get a signal back. And the signal is a little bit different to that we shine in. So we can distinguish between the laser that we put in and the light that comes out. Now we make that a little bit more. Okay, that's a picture of such a measurement. What you see here, these tiny points, are actually single NV centers in our diamond crystals. So how does that work? I want to explain you that a little bit in more detail. These are energy levels in our diamond. We start with the ground state. The electron is at the ground state. If we now shoot with our laser light on it, the electron will take some of the energy and jump up to the excited state. It won't stay there for long. It stays there for some milliseconds and jumps down, then back again. What we see then here is fluorescence light, light that we can measure, and we get information from that. Now we play the same game again, but we change the game a little bit. And we change it in the beginning. Let's start again with the electron on the energy ground level. And we use some microwave pulses to give the electron a little bit of energy. And what happens then is the electron changes its spin. You remember the picture I gave you, the compass needle, the little magnet in a magnetic field. if we invest some of the this microwave pulses a little bit of energy, and we turn and spin the qubit in an up position. So now we can, with these microwave pulses, initialize the qubit, whether it should be 0 or 1. And now we repeat the experiment from the left side, and something impressive happens. Now again, energy, the electron jumps up, but because we are coming now from a spin-up state, something different happens. It doesn't jump back down again and giving us the fluorescence light, but now it jumps to an intermediate state, stays there for a few milliseconds, and then jumps back down to the ground level. And the surprising thing about that is we don't see light. Or I should say, we don't see the fluorescence light we are looking for. So you see, now we can initialize a state. We can measure the state with our laser pulse. When we see light, we know the electron came from the ground state. If we don't see any light, the electron came from the spin-up state. And what we also can do is, if we choose the microwave pulse right, we can have a superposition. So coming back to the De Vincenzo criteria, we have well-defined qubits in our diamond. We are able to initialize to a pure state. We have qubit-specific measurements. That is our laser. So what we now need are quantum gates. So we need to calculate or do operations with the quantum computers. I show you an example, not for diamond, for another spin system, because that's a little bit easier to explain on one slide. But more or less, I guess you get the idea of how we are doing that with quantum gates. So I show you the controlled NOT gate, the C NOT gate. For the few of us who don't know what that is, we have a control bit. This is the red one, and we have a target bit, the blue one. If the control bit is 0, nothing will happen to the target bit. If the control bit is 1, the state of the target bit will be changed. So if we start with a 0, 0, we end up with a 0, 0. 0, 1 ends up with 0, 1. 1, 0 changes to 1, 1, and 1, 1 changes to 1, 0. So how do we realize? I mean, in a classical computer, you realize something like gates by transistors. How is that realized in a quantum computer? Well, I show you this with an example, with a model system of 2 coupled spins, an electron and a proton. And as you might know, this is a hydrogen atom. So we are doing now calculations with a hydrogen atom. Again, we're talking energy levels here. So we're starting with the lowest energy level would be the electron is down, the proton is down, lowest energy level. Corresponds to 0, 0 state. Electron down, proton up, 0, 1. Electron up, proton down, 1, 0. And both spins up, 1, 1 state. You already heard how we choose the spin of the electron. Electron transition, electron spin resonance. That was simply the microwave pulse that we are inducing, and by that choosing the spin of the electron. So now we can determine whether or not we have electron spin up and electron spin down. And now we do something that is called nuclear resonance, NMR. Again, electromagnetic pulse, but a different energy and frequency. And what we do here now is we choose wisely that the pulse has this energy here. And then we have exactly the C0 transition, because only if the electron is spin up, we will have a transition between those 2 states. So this is pretty in your face, actually. Okay, the idea of doing operations with a single atom might not really be in your face, but you see that how you actually do it is rather simple. You need one single pulse to do such a rather complicated logical gate, or realize such a complicated gate. Of course, I have to say, you just need a single pulse if you have a good spin system. That's, of course, what you need for something like this. Okay. In principle, I have shown you that we can have well-defined qubits, that we initialize to a pure state, how quantum gates could work in such system, and how we do qubit-specific measurements. But now I have started, or the title of my presentation says that I'm working with Diamond, and we are trying to realize quantum computers in Diamond. So your question should be, where is this guy getting his diamonds from? Are we mining them? Can we get them out of a mine? This is an old mine, an old diamond mine in Kimberley, South Africa. I like this picture very much, and this mine is long closed, like I think 1914 or something. But this is believed to be the largest hole that was digged by bare hands. So the people were actually getting the rubbish out there with their bare hands. So this is the biggest hole. Could we take diamonds from diamond mines? No, because I have already told you that we need very specific diamonds. We need them first to be very clear, very perfect, and then we induce very specific defects, the NV centers that we already talked about. So if we cannot find them in nature, of course, we make them by ourselves. So what we use there is a microwave plasma chamber. Funnily, it's not so different compared to the microwave ovens you have at home. It has the same frequency, it has the same power. The only difference is that we focus the microwaves very precisely in the middle of our vacuum chamber, and by that we can ignite a plasma in the microwave plasma chamber. And the plasma is actually is what you see glowing here. Why can we make diamonds from a plasma? Well, we use very specific gases. We use methane as a carbon carrier, CH4. You see here the carbon atom and 4 hydrogen atoms. And we use hydrogen because we need that for the chemistry. And what happens then here in the plasma ball is that we break those molecules and we have then the CH3 radical. And then we do something tricky. We offer those radicals a diamond surface. We call that the diamond seed crystals. We bring it close to the plasma, and then more or less like Lego playing by self-organization, this radical goes to the position on the diamond and continues to grow the lattice of the diamond. So we can start with a rather dirty one and start growing our perfect crystals on top of it. So does that really work? I want to convince you that that works because this is a video of our plasma chamber. You see this greenish plasma over the crystals here, and these are our dirty seed crystals. They have a heights of around 0.5 millimeter and a diameter of around 10 millimeters. So they're rather big. And okay, for this quantum computer application, we don't need really thick diamonds. But of course, if you have a lab and you have a plasma chamber in there and you have seed crystals, the first thing you do on a weekend where you don't have any other plans, you grow large diamonds. So that's nice that you clap your hands because I'm doing that from your tax money. Thank you. Okay, this is a movie. Let's see how these diamonds are growing. This is unfortunately, this is in a course of 3 days. Friday evening till Monday evening. Those diamonds don't look very nicely. Now they are 3 millimeters tall, so now they're really rather large-sized diamonds. Perfectly single crystals in the middle, not so perfect and not good looking in the outer edge here. So what I did is I took a laser and cut out the perfect diamond and went to a jewelry shop and asked them, because they really don't look like, you couldn't impress anybody with them. But I went to them and asked them if they can polish me the diamond like a real brilliant, like the stones you would have in rings or amulets or something. So the man there was suspicious because I had never seen such a stone. So he asked me what material that is. And I said, that's diamond. And then he said, where do you have it from? And I said, I made it by myself. We had issues, I would say. But I found somebody who was able to polish me the stones, and they look like this. They really look beautiful. Whenever I want to impress a crowd like you, I have a diamond, self-made diamond in my trouser. So if you want to take a look after the presentation, just come up to me and take a look. This is not really a perfect diamond, but it's enough to impress people. Yeah, right. Okay, we have perfect diamonds now, but the problem is, and we're coming to the end of my presentation, the problem is we don't want perfect diamonds. I told you we want NV centers in the diamonds. So how are we getting now the NV centers precisely in our perfect diamond crystals? Well, we take our ion guns. Something else that I buy from your tax money. We take ion guns, we take the perfect crystal, we take ion guns, and we shoot ions, nitrogen ions, obviously, on our crystals. And what happens then is, first, a pretty mess, so the nitrogen is in the crystal. And then we do something that we call annealing. We put the crystals at 700 degrees in some kind of oven. And then something happens, the nitrogen brings mechanical stress in the crystals, and the stress, the crystal wants to relax the stress. So what happens automatically, actually, is that the V centers, the vacancies, move to the nitrogen without us doing anything very professional with it. So that is one way how we can produce the NV centers in our crystal. The other method is called delta doping. I already showed you how we grow the diamond layer by layer, and that is shown here. At one specific time, we bring in nitrogen into the process. And then, of course, we deposit the nitrogen into our lattice. Now we have the nitrogen, but no vacancies. Now we take an electron gun, yet another thing I buy from your tax money. We shoot in vacancies here, do again the annealing step, and we end up with NV centers. Yeah. So now I'm really coming to the end. Well, I showed you that we have well-defined qubits. We have we can initialize them. I already showed you that. So we are able, in principle, to produce a diamond quantum computer. How far are we with that? What is the state of the art? Well, it's in its infancy, of course. So there was a 2-bit qubit quantum computer realized. Grover's algorithm was running on it, and 95. Okay, and the calculation was pretty right on the first try. If we really would want to decode our codes in a reasonable time, we need at least, or I read an estimation that we need 4,000 qubits to do that, and 4,000 perfectly entangled qubits is really not easy. But still, people are working on that. Based on Edward Snowden's documents, you see that the NSA runs a project worth 80 million called Penetrating Hard Targets. I like the name of it very much, to develop quantum computers. So I already told you that I liked the presentation, and that's really my last sentence now, the presentation of Andreas yesterday, and there was one remark that I want to repeat because I liked it so much. If you ask me, quantum computers are not there right now. They're not effectively working, but they will come because the technology already is there. It is very likely that those concepts, because you see they are rather complicated, the knowledge about the quantum computers will be in the hands of governments or rich companies. So it's very important that we keep an eye on the developments and what's possible and what's not possible. And yeah, to end on a positive side, I will keep an eye on that for you with your tax money. So thank you. Before we start with the question and answer, I have a podcast. If you like the way I talk about science, the podcast is called Methodisch Inkorrekt. I do it with my PhD students who suffers very much under me. So give him some love by downloading our podcast. Thanks.
Nice plug. Is this on? Oh, yeah, it is. Nice plug. Okay, so we have time for some Q&A. There's 4 mics in this room, 2 there, 2 there. Also, there's the ISC, of course. And we also, if you're unable to get up for like an actual medical reason, we have a backup audio angel to give you a mic. So we'll just start with number 2.
Okay, so thanks for the talk. My question is, can you realize entanglement between different NV centers, which I believe would be necessary to do more than 2-bit quantum computing?
First, before I answer the question, you're the first audience who's not asking about the diamonds and whether or not I'm rich because I'm producing permanently diamonds, but I appreciate that. Yes, there were realizations of entanglement of 2 qubits in diamonds and more than 2 qubits in diamonds. But what you're talking about is exactly the problem that we are having and what we are doing research right now on, because there are a lot of parameters that influence the stability of those qubits in a quantum diamond computer. For example, the distance between the qubits is a very important factor. The distance of the qubits to the surface of the diamond is a very important factor. The chemistry that is on top of the diamond crystal even makes a difference. So that's actually the problems we are working on. Yeah.
Okay, thanks.
Does the internet have a question? No, internet's still asleep.
Yes, the internet has a lot of questions. At first, I have to apologize for being imprecise. You spoke about the qubit-specific measurement, the part of the talk. The question is, what happens with the energy if the qubit does not drop to the lowest layer?
I think you mean when we're starting with the qubit up,
yes,
and
exactly.
yeah. I was pretending that there is no energy emitted, but that's of course not true. The energy has to go somewhere, but it is in a different frequency. So if we are just measuring the fluorescence light, or we're just looking at the fluorescence light we want to see, then we don't, in that frequency we don't see a light, but of course the energy is going somewhere else. So there will be light be transmitted, but in another frequency. So you don't see it, we don't see it.
And does this effect happen multiple times?
Yes, of course. Yeah, you can initialize your system again and start the process over again. And that is actually what's being done. You repeatedly initialize your system, measure it, and do that thousands and millions of times again and again. Yes.
And the internet is also interested if it happens if it happens from alone, or does the qubit drop by not being measured?
Yes, the qubit would also drop without being measured. That's one problem that we need to realize. We want to have stable qubits that keep their position as long as possible. But every once in a while, of course, the qubit will change by chance. So this is exactly what you need to control. You need to have stable systems that stay in the position that you want them to be for as long as possible. So, but you're absolutely right, and that makes it hard at this time to realize quantum computers, to have them stable over the time, yes.
Okay, thank you. Just a quick reminder, if you're leaving now, please be aware that there's a camera right there, so if you stand up in front of the camera, nobody's happy. So, okay, microphone number 1, please.
Well, first of all, thanks for spending our tax money in a really reasonable and totally cool way. So I was wondering, if we assume agencies with basically unlimited funding and highly compartmentalized information, do you see any practical risk that they, in air quotes, have the technology at scale and we simply do not know about it?
Yeah, I'm asked this question. I'm asked quite a lot, and of course, it's hard for me to really give an estimation about that. Usually, I would say I'm pretty. I have an eye on the developments that happen in science, or in my field at least. And what you usually see is that you have publications on one topic, and when it's really getting dangerous, those publications will drop, and you will not hear anymore about the findings in that field. And people, the experts that are working in these fields, are vanishing. So I would say optimistically, I don't think that they are much further, but I cannot say, maybe they are further than the publications suggest. Yeah.
With Stuxnet, we've seen that, or academia has said, some people have said that what was in Stuxnet cryptographically was years or even decades ahead of what academia knew about. So
yeah. That makes a little pessimistic view on the works I'm doing every day, but yeah, I hope you are not right, but I cannot, yeah. Thank you, thank you.
So if there's no talk by Nicholas next year, you know what happened.
I'm either really rich then or turn to the dark side. So. Yeah, right. The chances are really low. But,
Mic number 3, please.
Hello. Do you think there's a big difference between building a quantum computer with a few hundred bytes or a few thousand bytes? Because that's an important question, whether we should use elliptic curves. And do you have any estimation how long it will take till we have a practical quantum computer?
That's really tough questions, because this is really fundamental science right now, and we are really struggling with a few qubits, having them entangled for a longer period of time, or for a time that's enough to do calculations with that. And you see, we are like, this is really not like Moore's law, that we could say now we're at 10, and so we just calculate and say in 20 years we have the thousands that you need. There is so much fundamental physics to be done there on material science. I couldn't even tell you if a real working diamond or a quantum computer, there will be quantum computers, that's for sure, but will that be realized in diamonds? I cannot tell you, because there are so many problems. Just what you said, if you're starting with a few quantum bits, they disturb themselves, and so it's getting increasingly difficult if you increase, starting with 4 qubits going to 8 or 16. So that's really hard. I don't dare to give you any numbers if that will be possible in the future or even when it will be possible. So I'm sorry.
And can you say something like, is it much more difficult to build 4,000 compared to 400 bits? That's really important for the cryptographic implications.
Since we haven't realized 400, I'm not sure if we find methods that will scale. That's the question. If we find methods to produce, I mean, we are really struggling to bring in precisely 4 or 8 in a specific distance from each other. So yes, when we have the methods to make it with 8, maybe it's possible to make it with 400, and then we are at 4,000. But I see no technology now that is scalable to do that. So right now, I don't know how. Thank you.
Mic number 1, please.
You really often talked about the state of the quantum bits in the diamond. How long of a time period you're talking about? They stay stable.
Some milliseconds. So I think from the one publication that I showed, they stated something like 2 milliseconds. But that's enough to do some calculations. That would be enough, yeah. And then again, like the question before, we can initialize them again and do the calculation again. But that's again something that we are working on is to improve that time to make more calculations after the initialization.
How about the internet?
Yes, one question is, or you talked a lot about our tax money. Do you publish in open access?
Yes, I try to. Yeah, my last paper, not on diamonds but on graphene, was published open access. So I really suffer from the publication system. I feel your pain. So I think it's really. It's a shame that you are not able to access the publications. The funny thing is, not even I am able to access all of my publications that I published some years ago because we canceled the subscription of the journal, so I cannot access my own papers, and that's absolutely bullshit. So the whole system is fucked up. But. But to be fair, the European Union is changing the system a little bit. Now when I'm funded by European money and also German money from funding agency, they expect that the science that I do will be published open access. So there is something going on in that field. So that's not so pessimistic, or it's getting better there, at least.
Mic number 2, please.
You said you would watch the market for us. I've got a question about D-Wave. Do they have a quantum computer that conforms to your criteria?
I mean, D-Wave is a company, and so they are not publishing what they have. So it's really a little bit difficult to get real hard facts on that. But from everything I know or I see, they have a different realization of the quantum computer. They have something that is called adiabatic quantum computer. The real difference there is that they are not working with, as far as I understand it, with really entangled qubits. So they haven't realized the power, or they haven't set free the power of a real quantum computer. As I said, it's really hard to get information there, but from everything I have read, this is not a pure quantum computer that I have suggested today here. But this is, of course, something, I mean, this is a big company, there are big companies behind that, and there is money, and they are at least working on the realization of the principle. So this is what I wanted to say with the last sentence. So we need to be aware of that people are working on that, and people with lots of money. So they are not there yet. This is not a quantum computer I'm talking about, and the quantum computer that will crack all our passwords, but people are working on that.
Mic number 3, please.
You presented 2 different methods how you get the nitrogen and the gaps in the diamonds, and in the pictures we saw different orientations of the nitrogen and the gaps, and I was wondering if it makes a difference, and if so, if you can influence what is the orientation.
It makes no difference, and we don't have influence. Like you saw, it's more like a random process. So we shoot the ions in there or incorporate the nitrogen, and then make this tempering step. And this is a self-organizing process. This is actually this is the hard thing, or we are working on that. So I'm funded by this Mercator research. Funding agency, and that is the task that we are working on right now, is how are we able to put the NV centers at a specific positions where we want to have them, but that is not orientation but position, and how can we how is that influencing the performance of the NV centers in our diamond? In the end, there is not. When it comes to the orientation or this annealing step, there is no control, if you want, like that. I mean, we have some process control of course, temperature and basically temperature to make this more efficiently, or let the vacancy move faster and give them more energy to move. But that's all. Yeah. Thank you.
Okay, we are unfortunately out of time, so I have to officially shut this down, but Nicholas is still here, so if you have questions, just come up. Thank you.
Thank you.
Please use the front exit.